Hello, my name is Giovanni di Crescenzo. I'm going to present secure and efficient delegation of elliptic-curve pairing. This is joint work with Matluba Kojoeva from CUNY in New York, USA, Delaram Karobey in University of York in York, UK, Vladimir Spielrein from City University of New York in New York, USA. My affiliation is Prospecta Labs in Basking Ridge, New Jersey, USA. And you might have heard us about few years ago, at least under different names, Telcordia, Applied Research, Bellcore, Bell Labs. I'm going to talk about delegation, and in my first slide, I really want to make the case that delegation is very fitting with today's recent computing trends. Delegation has been studied for many years, but these computing trends are more recent, and still delegation is fitting really well. And the two computing trends I'm talking about are cloud computing and Internet of Things. So I wanted to look at some of the statistics, or at least estimates for them 1 or 2 years ago. And I was very impressed. If you just go, you can read the numbers, but if you just go by market size, you see that global cloud computing is expected to reach 600 billion by 2023. And the IoT device market is expected to reach 1 trillion by 2026. Now, arguably, these are pre-COVID statistics, but they are certainly indicative of where the trends are going. And so, why am I making the point that delegation is very fitting? Because cloud computing gives you this abundance of servers with incredible computing power, much bigger amounts of computing power than the devices usually use. And Internet of Things, on the other hand, gives you this abundance of devices with medium to small to incredibly small computing power and resources in general. And so it's very fitting that such weaker devices seek the help of the stronger cloud devices to perform computation. And the theoretical model that we've been using for many years in the area with slight modifications here and there is essentially that of two parties, a client, which is computationally weaker, and a server, which is computationally stronger. And the client has an input X and would like to compute f of X or some function F that is known to both client and server with help from the server. F can be any function. We'll mainly deal with functions that are used in cryptography and that they seem relatively more expensive. The interaction model is that the client sends a message to the server performs heavy computation, sends back a message to the client performs weak computation to recover f of X. That's the online phase. We always try to use an offline phase that will be very advantageous to design efficient protocols in the online phase. And we can think of the offline phase where the client device is being deployed. And so in that moment, in that phase at least, the client should not be expected to be computationally limited. So in that case, some more intensive computation can be performed. The requirements that we expect from these protocols are correctness, easy to satisfy at the end of the protocol if it's executing with compliance to the specification, then the client will return f of X. Privacy of the input, only minimal or no information about the input X should be revealed to the server. Security of the output says that no malicious server should force the client to output something that is different than f of X, possibly except with small probability. And notice that I'm not restricting the power of the adversaries, both for privacy and security. And this is, just for sake of generality. Of course, I could restrict them to polynomial time, but for sake of generality, all our results will hold regardless of any power restriction on the adversary. Efficiency, there are many efficiency requirements, of course, one can think of. I'll just focus on perhaps the most important ones. We want the client's runtime in the online phase to be much smaller than computing f of x from scratch. Otherwise, there will be no point in delegating, right? So also the communication is important. This is not often mentioned. The communication between client and server should also be not too high. Let's say not much higher than the value f of x itself, right? That seems some kind of a lower bound there. And finally, the runtime by the server, yeah, that's also important. It wouldn't be a good protocol if we were really requiring the server to do a huge computation, much bigger than actually computing f of x. So the function that we're going to delegate here is the pairing function. It's a well-known primitive in so many cryptographic protocols. The most important property that it needs to satisfy is this, the bilinearity, meaning for all A in group G1 and B in group G2, group G1, G2 are the domain, the input domains. And for any integers R and S in ZL, L is a large prime that denotes the group for the additive cyclic group G1 and G2 and the multiplicative cyclic group GT, the target of the map. This equality is satisfied, right? That's the bilinearity property. Now there is a trivial map that satisfies that bilinearity property, but this is why we require this non-triviality condition that rules out that trivial map. Of course, the map has to be efficiently computable. So these maps are used a lot in cryptography. First of all cryptography protocols based on discrete logarithms can usually be reformulated to work using pairings, and that results in great space savings. Very useful in some applications. Not only that, but there are many new capabilities that are made possible thanks to pairings. I'll just mention a couple really. They were object of famous prizes, identity-based encryption by Bonnet and Franklin in 2001, and Jou's three-party key agreement, an extension of the Diffie-Hellman key agreement protocol to three parties from the 2000 year. Some practical considerations. So the early constructions based on wheel pairing were not so efficient. So it was quickly noticed that pairings were, let's say, much less efficient than, let's say, group exponentiation, which we were using much more back then. So then more and more efficient constructions have been proposed, Tate pairings, and most recently 8 pairing variants. Now, even after those variants, so by the way, the current most practical pairing realizations use an elliptic curve defined over a field FP for some large prime P. But even those most efficient will still seem to satisfy a property that pairings are, let's say, almost 1 order of magnitude more expensive than exponentiation in that group. Also, it's fair to say that exponentiation in GT is really the most expensive operation among the 3 group operations. It's more expensive than scalar multiplication in G2 and even more than scalar multiplication in G1. Previous results, there are so many results on delegations of various operations like exponentiation in cyclical RSA groups, large matrix multiplication, and even arbitrary functions with very, very large circuits. But with respect to pairings, which is the function we consider here, these are the papers that gave previous results. There were some results that gave no result security. They were not considering result security as a requirement yet. Then there were some results that consider result security, but as pairings have become more and more efficient, that efficiency makes those protocols not more efficient than the non-delegated computation. Now there's one paper actually in ACNS 2014, which is kind of the best result. And it gave the first method that is more efficient even today than non-delegated computation for the KSS elliptic curve, but not for the BN elliptic curve, which seems to be one of the most recommended curves. So in our paper, we gave the first pairing delegation protocols that satisfy input privacy, result security, and efficiency with respect to all four of the most studied elliptic curves, including BN, and in several input cases, depending on which of the two inputs A and B are public or private. If they're publicly available to all parties, including the adversary, or if they need to remain private from, let's say, the server. Or they're known only in the online phase, or they're already known in the offline phase. Okay, so we do have 5 main protocols. You see here in table 1, depending on, again, some of these different cases for the two inputs A and B. We can extend this, using these protocols, we can essentially cover all possible cases. And you see the average improvement that we have over the previous best goes between 1.75 and 5.55. And over the non-delegated computation goes from 1.31 to 9.41. Really, our main improvements are on the first 3 input scenarios where at least one of the 2 inputs is known in the offline phase, which is after all a very common scenario. Think of public key cryptography, where let's say one of these 2 inputs is in the public key, and that's an offline input there, as opposed to an online input, which could be a ciphertext, a value in a ciphertext, or a value in a signature. This last column in the table tells you that indeed there are many cryptographic protocols where you really meet a computation of a pairing in that particular input scenario. Let's say A public online, B public offline. And we only included some here, but there are many papers that with these input scenarios. Now, what else? So our improvements are also qualitative in some sense. So for instance, in protocol 1 and 2, the most expensive operation from the client is a short 128-bit exponent exponentiation, and no such protocols have been previously offered in the literature. And actually, in all of our protocols, the client only performs 1 or 2 short exponent exponentiations. And in the past work, there were always full domain exponentiations. So that's a full domain exponentiation takes more than 2 short exponent exponentiations in GT. So let's look at our first protocol. Our first protocol is actually when both inputs are public, so there really is no privacy requirement. But still, the hard to achieve requirement is that of security. So in particular, for each of these, for our 5 protocols actually, we need to build some new probabilistic tests that the client uses to check what the server is sending to the client. The server could send anything, right? So, and the client, sure, the client could recompute pairings, but then that defeats the purpose, right? So we want a client that does not compute pairings. In fact, we try to even avoid a client that computes full domain exponentiations, and we achieve successfully to do that. So this is the protocol on the right, reasonably short and simple. Simplicity is a goal. We want the client to be as simple as possible, the client's program. The probabilistic test is here in this rectangular box, and essentially says that you can basically define a probabilistic equation, and based on the values returned by the server. In particular, E of Z1B is the W1 that is returned by the server, And E of AB is also the W0 returned by the server, and it's actually the output that the client will return. So those are checked against a value E of U1B that is computed offline by the client, where U1 is random. And Z1 also combines combines the input A and the random value U1. So the result security follows by proving that if U1 is random, then the Z1 sent by the client will not leak the randomizer B, the challenge randomizer B, which is the short exponent. And then that if the server sends an incorrect W1 prime, then it can only pass the probabilistic test with probability 2 to the minus lambda. Lambda is a statistical parameter and is also the length of the randomizer B. And so we can pick that. We set it as 128 in the computation of our performance, but in practice, people use much smaller statistical parameters. So our protocols are actually much more efficient, or a bit more efficient than the numbers that we show. And the table 3 tells you the improvement with respect to the previous best. In particular, the last 4 columns are columns with respect to the 4 recommended, recently recommended elliptic curves. You see BN12 and KSS 18, and a ratio T sub C, T of sub C divided T sub F is the ratio of the client's computation to the runtime to compute the function. So that's the first protocol. The second protocol considered the case of A private, and it has a more involved probabilistic test. And now, in addition to security, we need to prove that indeed A stays private. And if you look at the protocol, the server will send W, so the client will serve Z0 and Z1, which contains A, but Z0 and Z1 are really masking A with 2 randomizers, U0 and U1. And those randomizers are random enough to also mask the challenge B that will be used in the probabilistic test. So the probabilistic test continues to hold and to imply security, but we also achieve privacy of A. Of course, there is a slight more work to do from the client, but still very little work. And table 4 gives you the improvement over the previous best results. Our third protocol considers the case of A and B being both private, A private online, B private offline. Slightly more complex probabilistic test. I don't have much time to go over it, but we use a further randomization trick that does require some additional computation, in particular some scalar multiplications in G1 and G2, and this is why this protocol is less efficient than the previous 2, but still significantly more efficient than the previous best work. Running out of time, so our fourth and fifth protocol are consider the case of both A and B are online, and really we didn't investigate this much. Really, we really thought, can we combine the previous 3 protocols to give some protocols also in the case when A and B are online? And the answer is yes. The combinations are kind of straightforward to some extent, so they are not really optimized. But even those combinations do improve over previous work. But on the other hand, for instance, in the case of BN, the 5th protocol is not faster than, goes beyond 1, as you see. The ratio is beyond 1, so this means it's not faster than non-delegated computation, but for BN, but it is faster for the other 3 curves. I think I have to conclude, running out of time. So we show techniques for a computationally weaker client to efficiently, privately, and securely delegate bilinear pairings to a single possibly malicious server. Efficiency gains can be up to almost 1 order of magnitude, regardless of which of the most practical elliptic curves are used for the pairing delegation. Best improvements are in the scenarios where at least one of the 2 pairing inputs is known in the offline phase, which is a common scenario. Our techniques improve the state-of-the-art on all input scenarios and are actually applicable to essentially all known pairing-based cryptographic protocols. Thank you for your attention.